All right, you ready for this? We're going deep on how Earth went from a molten MSS to the planet we know and love.
Oh, yeah.
Buckle up, because we're talking billions of years,
Billions.
crazy cosmic collisions,
Mm.
and a whole lot of lucky breaks.
A lot of luck involved.
You wanted to understand how Earth formed and became habitable, so we dug up this awesome educational video. It's like watching a cosmic documentary unfold, and trust me, you're going to want to hear this.
It all starts about 4.6 billion years ago
Okay.
with this massive cloud of gas and dust
Oh, wow.
just chilling in space. We call it the solar nebula.
So picture this, right?
Huh.
A massive swirling cloud of hydrogen and helium,
Right.
the most basic building blocks of the universe.
Exactly.
It's like a giant cosmic nursery for stars and planets.
It is.
But here's where things get interesting.
Okay.
A nearby star goes supernova.
And when I say supernova, I don't mean the Big Bang.
Right.
This is a different kind of explosion. But equally important for our story, the shock waves from this supernova
Oh, wow.
slam into the solar nebula,
Okay.
causing it to collapse and start spinning. Think of it like a cosmic pizza dough being tossed and spun.
Okay.
That spinning motion creates something called a protoplanetary disk.
Protoplanetary disk.
It flattens out like a disk.
Right.
And that's why our solar system is relatively flat today.
That makes sense.
And of course, most of the material from that nebula ends up clumped in the center,
Yeah.
forming our very own sun.
And get this.
Yeah.
The sun grabs a whopping 99.8% of all the material in the solar system.
It does.
So that leaves a tiny fraction, just 0.2%.
For everything else.
For everything else, exactly.
That's where all the planets, moons, asteroids, comets, everything. But here's where things get really interesting. This leftover material doesn't just sit there.
No.
It starts to clump together.
In a process called accretion. You see, those tiny dust particles are constantly bumping into each other and sticking together. It's like cosmic dust bunnies just getting bigger and bigger over time.
Exactly. Over millions of years, they form larger clumps called planetesimals, which are like mini planets. And then, with more collisions and gravity's pull, those planetesimals combine to become protoplanets about the size of our moon.
Wow.
Think about it. This accretion idea was once dismissed as something out of science fiction.
But now we see it happening all over the universe. It's like watching planets being born. And the proof is right here in our solar system.
Yeah.
When we study meteorites,
Right.
we're actually looking at ancient dust from before the planets formed. They're like time capsules from the very beginning.
Amazing what we can learn from those space rocks. So we've got these protoplanets forming,
Yeah.
but things are far from peaceful. This is the Hadean Eon,
Okay.
and Earth is going through its teenage years.
And let's just say, those teenage years were rough.
They were rough.
We're talking constant collisions between protoplanets, huge impacts that melt rock and create a global lava ocean.
They named it after Hades,
Oh, wow.
the Greek god of the underworld.
Right.
And for good reason. It was a truly hellish environment.
It sounds it.
But amidst all that chaos,
Okay.
something incredible happened. Earth got its water.
Wait a minute. Are you telling me those same impacts that made Earth a molten wasteland also brought us the key ingredient for life?
They did.
That's mind-blowing.
It is. Many of the comets and asteroids that bombarded Earth were carrying a precious cargo, ice. Over time, all those icy impacts delivered vast amounts of water to our planet, forming the basis for our oceans.
That's incredible to think that the very forces that created such a hellish environment
Right.
also brought us the very ingredient that makes life possible.
It did. It's amazing.
So we go from a lava world to a water world.
Yeah.
But what about all that molten rock? How did Earth layers form out of all that chaos?
Well, think of it like this. As Earth started to cool down, and we're talking millions of years here,
Right.
heavier elements like iron and nickel sank towards the center, pulled by gravity.
Okay.
That's how the core formed.
And the lighter elements rose to the surface, creating the mantle and eventually the crust. It's like a giant planet-sized lava lamp with everything separating out. This process is called differentiation.
Right.
And it's how Earth got its layered structure, much like the one we see today.
Precisely. And it's more than just a simple crust, mantle, core situation. Each layer has its own unique properties and composition. It's fascinating.
Yeah.
But there's another major event we need to talk about.
What's that?
The formation of our moon?
Oh, yes, the moon. It's not just a pretty face in the night sky.
No.
It plays a crucial role in making Earth habitable.
It does.
How did that come about?
The prevailing theory is the giant impact hypothesis. Picture this. A Mars-sized protoplanet named Theia slams into early Earth.
Hold on, a planet-sized collision? That's insane.
It was a cataclysmic event. Wow.
It's believed that the cores of Earth and Theia merged while a massive amount of debris was flung out into space.
Oh, wow.
That debris eventually coalesced to form our moon.
So without that colossal collision, we wouldn't have the moon. That's wild.
That's right.
It literally shaped our planet and its future.
Exactly. The moon's gravitational pull is crucial for stabilizing Earth's axial tilt, giving us those predictable seasons we rely on for agriculture. And its pull creates tides, which were vital for life to transition from oceans to land.
So the moon isn't just a pretty sight. It literally shaped our planet and made it suitable for life as we know it. Incredible. Now, we've got the Earth's layers, the moon in place, but what about the air we breathe and the oceans? We can't have life without those.
You're right, and that's where volcanic activity comes in. Intense eruptions spewed out gases, forming Earth's early atmosphere.
Was it anything like the air we breathe today? Not quite. It was a toxic mix of gases like water vapor, carbon dioxide, methane, and ammonia. Definitely not breathable for us. But as Earth cooled, the water vapor in the atmosphere condensed, and it rained for millions of years. That's how our oceans formed.
So imagine a constant planet-wide drizzle. For millions of years, that's a lot of rain.
Yeah.
And those newly formed oceans started absorbing carbon dioxide from the atmosphere.
Exactly. The oceans acted like a giant carbon sink, paving the way for oxygen to eventually become the dominant gas in our atmosphere. Without those early oceans, Earth might have ended up like Venus, a scorching hot planet with a runaway greenhouse effect.
It's amazing to think how crucial our oceans are, even today. They helped regulate the climate and create conditions for life to emerge. But that's a story for another time.
Indeed. But for now, we've laid the groundwork. We've seen how a chaotic cloud of gas and dust transformed into a planet with oceans, continents, and a moon. It's a remarkable journey, wouldn't you say?
It really is. It's amazing to think that all these events, from supernova explosions to giant impacts, played a role in shaping the world we live in today.
And that's just the beginning. We haven't even touched upon the emergence of life itself. Are you ready to dive deeper?
Absolutely. I'm hooked. This is one incredible story, and I can't wait to see where it goes next.
It's mind-boggling to think that those vast oceans formed from billions of years of rain were the cradle of life as we know it.
Yeah, it's like something out of a science fiction novel,
Okay.
but it's real science.
It is.
So how do we go from a water world to actual living organisms? What sparked that transition?
Well, that's the big question that scientists are still trying to answer,
Yeah.
but one of their leading theories is the RNA world hypothesis.
Right.
See, RNA is a molecule very similar to DNA,
Right.
which carries our genetic code.
Okay, RNA, I remember learning about that.
Yeah.
It's like a simpler version of DNA, right?
Exactly. And scientists believe that RNA might have been the first self-replicating molecule on early Earth. Imagine those early oceans teeming with a rich soup of organic molecules.
Right.
The idea is that RNA formed spontaneously in that environment
Okay.
and started to make copies of itself.
So before DNA took the stage, RNA was the star of the show,
That's right.
running the whole operation in those primordial seas.
Precisely. And over a vast expanse of time, these RNA molecules evolved
Right.
and eventually gave rise to DNA and the more complex life forms we see today.
Wow.
It's fascinating to think about. This single molecule could have been the starting point for all life on Earth.
It's like a giant game of telephone. But instead of words, we're passing down genetic information over billions of years.
That's a great analogy.
It's amazing. But I have to wonder, how did those early life forms survive in that harsh environment?
Yeah.
Wasn't the early Earth a pretty tough place to live?
Oh, absolutely. The atmosphere is still evolving and the oceans were likely quite acidic.
Yeah.
But life, as we know, finds a way.
Life finds a way. That sounds familiar. But seriously, what were some of the key adaptations that allowed life to thrive in those conditions?
Well, one of the most significant adaptations was photosynthesis.
Okay.
Early microorganisms like cyanobacteria evolved the ability to harness energy from sunlight.
Photosynthesis, like what plants do to make food, right?
Exactly.
So these tiny bacteria were like the first solar panels on Earth, soaking up that energy from the sun.
That's a great way to put it. And here's where things get really interesting.
Okay.
Photosynthesis doesn't just produce energy for the organism,
Right.
it also releases oxygen as a byproduct.
Wait a minute. So these early bacteria were pumping oxygen into the atmosphere.
Yes.
Isn't that what eventually made Earth habitable for oxygen-breathing creatures like us?
You got it.
Mhm.
Over billions of years, these photosynthetic organisms gradually transformed Earth's atmosphere from a toxic mix to the oxygen-rich air we breathe today.
Wow.
It was a slow process, but a truly monumental one in our planet's history. They quite literally changed the world.
That's incredible. It's amazing to think that these tiny microscopic creatures were responsible for such a massive change on a planetary scale. Talk about punching above your weight class.
Right.
But what happened next? We've gone from a molten ball of lava to oceans teeming with microscopic life. But how did we get from single-celled organisms to all the diversity of plants and animals we see today?
That's where the story of evolution gets even more complex and fascinating. We're talking about billions of years of change with countless twists and turns along the way.
Yeah.
But one of the key milestones was the Cambrian explosion.
The Cambrian explosion, that sounds pretty dramatic. What exactly exploded?
Well, it wasn't a literal explosion, but more like a sudden burst of evolutionary innovation.
Yeah, okay.
Around 540 million years ago, we see a dramatic increase in the diversity and complexity of life.
So like evolution went into overdrive.
Exactly. It's thought that a combination of factors created the perfect conditions for this evolutionary burst. Changes in ocean chemistry, the availability of new ecological niches, and even the evolution of new genes that allowed for greater complexity.
Wow.
Suddenly, we see the first appearance of many of the major animal groups that exist today.
Wow. So life went from simple to spectacular in a relatively short amount of time. From there, it's this incredible journey of evolution, ultimately leading to all the amazing creatures we see today, including us. It's hard to wrap my head around such a vast timescale.
It really is remarkable.
Yeah.
And the Cambrian explosion gives us a glimpse into the incredible power of evolution.
But just to be clear, we're talking about the appearance of very early versions of those animal groups, right? Not fully formed jellyfish and vertebrates swimming around as we see them today.
That's right. It's important to remember that evolution is a gradual process.
Right.
The Cambrian explosion marks the point where we see the first evidence of these body plans and lineages. They would continue to evolve and diversify over hundreds of millions of years, leading to the incredible variety of life we see today.
So those early forms were like the prototypes, the rough drafts of the animals we know and love today.
Yeah.
It makes you wonder what those early creatures would think if they could see their descendants now.
It does make you wonder. And it highlights just how much our planet has changed over time.
Yeah.
The Earth those creatures knew was a very different place than the one we inhabit today.
That makes me think about something else the video mentioned.
Okay.
The Earth's layers. It turns out it's not just a simple crust, mantle, core situation.
Right.
There's more to it than that.
Absolutely.
Hmm.
What we learn in school is a simplified model.
Yeah.
In reality, there are 5 distinct layers based on their physical properties.
Okay.
We have the lithosphere, the asthenosphere, the mesospheric mantle, the outer core, and the inner core.
Okay, I'm all ears. Break it down for me. What are these layers all about?
Well, let's start with the lithosphere. This is the outermost layer, the one we're most familiar with. It includes both the oceanic and continental crust,
Right.
and it's broken up into tectonic plates.
Oh, right, the tectonic plates, the ones responsible for earthquakes and volcanoes.
Exactly.
So are those plates just floating on top of the mantle?
Not exactly. They're actually embedded in the uppermost part of the mantle, which brings us to the asthenosphere.
Okay.
This layer is incredibly interesting because it's partially molten.
Partially molten, so it's kind of like gooey rock.
You could say that. It behaves like a very viscous fluid,
Right.
allowing the lithospheric plates to move and interact.
So it's like a lubricant for those massive plates.
Think of it as a slow-motion dance happening beneath our feet with these enormous plates shifting and grinding against each other.
Yeah.
No wonder we get earthquakes and volcanoes.
So what's going on beneath all that action?
Deeper down, we encounter the mesospheric mantle.
Okay.
This layer is more rigid and less mobile than the asthenosphere. It's a transition zone where the rocks become denser and the pressure increases dramatically.
Makes sense. The deeper you go, the more intense the pressure. And then we finally reach the core, that super hot heart of our planet. What's going on down there?
The core is actually divided into 2 parts, the outer core and the inner core.
Okay.
The outer core is made up of liquid iron and nickel and is constantly churning due to the intense heat.
And all that churning is what generates Earth's magnetic field, right? the one that protects us from harmful radiation from the sun.
Exactly. It's like a giant invisible shield surrounding our planet, deflecting charged particles from the sun.
Wow.
Then at the very center, we have the inner core. It's also made of iron and nickel,
Okay.
but it's solid.
Wait, solid. But isn't it incredibly hot down there?
It is. The inner core is estimated to be around 5,200 degrees Celsius, which is hotter than the surface of the sun.
Wow.
But the pressure at the center of the Earth is so immense that it forces the iron and nickel atoms into a tightly packed solid structure.
So it's like a solid ball of metal spinning at the heart of our planet.
It is.
That's mind-blowing.
It really is. And here's another interesting tidbit. The inner core is actually growing over time
Really?
as the liquid outer core slowly cools and solidifies.
So the Earth is constantly evolving even deep beneath the surface.
Absolutely. And the more we study these layers, the more we understand about our planet's history, its dynamics, and how it became the life-sustaining world we call home.
Wow.
But I think it's time we shift our focus back to the story of life itself. Are you ready to explore how those early organisms paved the way for the incredible diversity we see today?
You bet. I'm eager to learn more about how those early life forms evolved and diversified. Let's continue our deep dive. Okay, so we've talked about Earth's fiery birth, formation of the moon, the emergence of oceans, and even those early microscopic life forms.
Right.
It's been quite a journey.
It has.
But what happened next? How did we go from those single-cell pioneers to the incredible diversity of plants and animals we see today?
Well, we're talking about billions of years of evolution.
Right.
A story filled with twists and turns, adaptations and extinctions.
Yeah.
It's a complex and fascinating tapestry of life.
And somewhere in that tapestry is the story of how those early oxygen-producing bacteria
Yes.
paved the way for more complex life forms.
Exactly.
It's incredible to think that those tiny organisms played such a crucial role in shaping the world we live in today.
Absolutely. Their contribution was monumental. As oxygen levels rose in the atmosphere,
Yeah.
it created opportunities for new life forms to evolve.
Yeah.
Organisms that could utilize oxygen for energy.
Right.
This led to a cascade of evolutionary innovations.
So it's like one change led to another,
Yeah.
setting off a chain reaction that ultimately resulted in the incredible biodiversity we see today.
Precisely. It's like a domino effect, with each evolutionary step creating new possibilities for life to explore.
I'm curious, though.
Yeah.
Did all those early life forms thrive in this oxygen-rich environment? It seems like such a dramatic change to the planet.
It was a dramatic change. Yeah.
And not all life forms were able to adapt. For
Right.
some, oxygen was toxic.
Oh, wow.
They were adapted to a world without it.
Right.
And this shift in the atmosphere led to their declines.
So while it was a boon for some, it was a bust for others.
Exactly.
It's a reminder that evolution isn't always about progress. It's about adapting to whatever challenges and opportunities the environment throws at you.
That's a great point. Evolution isn't a linear path.
Right.
It's a branching tree with countless possibilities.
And somewhere on that tree, our own lineage emerged. It's mind-boggling to think about all the twists of fate and evolutionary innovations that had to happen for us to be here today.
I know, right?
It really puts things in perspective, doesn't it?
It does. Our existence is a result of billions of years of cosmic and biological processes.
Yeah.
It's a story of chance and adaptation, of extinctions and diversification.
So from a fiery ball of molten rock to a planet teeming with life, it's been quite a journey.
It has. This deep dive has been incredible, and I feel like I have a whole new appreciation for our planet's history and the intricate web of life that calls it home.
It's been a pleasure exploring this incredible story with you. And remember, this is just a glimpse into the vastness of Earth's history. There's still so much more to discover and learn.
Absolutely. And that's what makes it so fascinating.
It is.
Who knows what other secrets and surprises are waiting to be uncovered? It makes you wonder, what will the next chapter of Earth's story hold?
That's a question for the ages. But one thing is certain, Earth's story is still being written, and we're all part of it.
Well said. And on that note, we'll wrap up our deep dive. Until next time, keep exploring, keep learning, and keep wondering about the incredible world we live in.